Hello everyone. My name is Sazan Azizian, and I am with the College of Science and Technology at Bellevue University. Today, I am pleased to present our paper, titled Neural-Symbolic Multi-Objective Optimization for Performance-Aware ORM Database Design. This work is a collaboration with Dr. Ayub Hazrati from the Vanguard Group, Artin Azizian from McGill University, Dr. Elam Rastegari from Creighton University, and Dr. Hamid Bagheri and Dr. Wan Chui from the University of Nebraska-Lincoln. In this work, we present YMAP, a neural-symbolic framework for selecting valid and efficient ORM database designs. I will first explain the motivation and research gap, and then present the YMAP framework and its main evaluation results. ORM frameworks translate object-oriented models into relational database schemas. However, the same object model can be mapped in several valid ways. On the right, the customer order example shows that inheritance and associations can be represented using join subclass, flattened, or join table mappings. All of these can be correct, but they create different database structures and different performance behavior. One schema may support faster queries, another may support faster inserts, and another may use less memory. The problem is that ORM tools often rely on defaults, and finding the best design can require benchmarking many candidates. So the question is, how can we select a valid and high-performance ORM schema without benchmarking every candidate? I will use this example as the running motivation for YMAP. Existing approaches solve only part of the ORM design problem. First, symbolic synthesis can generate valid database schemas and guarantee that they follow the required mapping rules. However, as the object model becomes larger, the number of possible schema designs grows very quickly. Second, benchmarking methods can measure the real performance of each design. However, they require creating the database, loading the data, and running the workload for every candidate. This process is accurate, but it is expensive and time-consuming. Third, learning-based methods can make the selection process faster. However, many of them use course labels or rankings instead of predicting detailed performance values. Therefore, the main research gap is the need for a method that guarantees valid ORM schemas while also predicting their performance efficiently. This is the motivation for YMAP, which combines symbolic validity with continuous neural performance prediction. Now, let me explain the YMAP framework step by step. First, YMAP receives the software object model and the ORM mapping constraints. For example, in the customer order model, the constraints describe the inheritance relationship, the association between customer and order, and the mapping strategies that are allowed. Second, Alloy uses these inputs to generate only valid database schemas. These candidates may use different mapping strategies, such as join subclass, a flattened single table design, or a join table association. Although their structures are different, all candidates preserve the original software model. Third, each valid schema is automatically converted into a standardized SQL DDL representation. YMAP also extracts simple symbolic features, such as the number of tables, foreign keys, join tables, and inheritance depth. Next, the DDL is analyzed by three pre-trained encoders: GraphCodeBERT, CodeT5+, and LLaMA. Each encoder captures a different view of the schema. Their representations are combined with the symbolic features. This combined representation is then passed to a lightweight regression model. The model predicts three continuous performance values: insert latency, query latency, and memory footprint. Finally, YMAP uses these predictions in one of two ways. It can return a Pareto set of several strong trade-off designs, or recommend a single schema based on the developer's priorities. The important point is that profiling is used during offline training, but during inference, YMAP does not need to deploy and benchmark every candidate schema. The three encoders provide complementary information. GraphCodeBERT captures structural relationships, CodeT5+ captures DDL syntax and coding patterns, and LLaMA captures broader semantic context. YMAP combines these three representations into a unified schema. This representation is then used by the trained regression model to estimate performance. The important point is that the large pre-trained encoders remain fixed. Only the smaller regression head is trained on the offline profiling data, which reduces the training cost. This slide summarizes the evaluation. We evaluated YMAP on 9 object models from e-commerce, banking, and healthcare, with 100 to 2,700 valid schemas per model and about 9,500 labeled schemas. For Pareto quality, YMAP achieved the lowest generational distance, 0.01, and the highest hypervolume, 0.91. This means its predicted Pareto set is closer to the ground truth frontier and covers better trade-off regions than Lent and DTS. For efficiency, YMAP reduced inference time and memory usage. It required 900 seconds and 6.2 gigabytes of peak memory, compared with 26,000 seconds for Lent and 3,400 seconds for DTS. The takeaway is that YMAP more accurately approximates the Pareto frontier while lowering inference cost. Thank you. I will be happy to answer questions now, and please visit our poster for a more detailed discussion.